Welcome to the Explainer. Today, we're jumping into a really common coding problem, but we're going to tackle it from two completely different angles. First up, we'll look at the super intuitive sliding window technique. Then, we'll switch gears to the more powerful prefix sum with a HashMap method. By the end of this, you'll know exactly which tool to pull out of your toolbox and when. Let's get right into it. So let's set the stage. Imagine you've got a list of numbers, right? And your mission, should you choose to accept it, is to find the first continuous block of numbers that adds up to a specific target. Think about it like a list of game scores, and you need to find the first winning streak that totals exactly 100 points. That's the challenge we're solving today. Before we go any further, let's make sure we're on the same page about one key term, subarray. This isn't just any random group of numbers from our list. It has to be a continuous, unbroken chain. So for the array 1, 2, 3, 4, 2, 3 is a perfect subarray. But 1, 3? Nope. They're not neighbors, so that doesn't count. We're looking for a solid slice. All right, let's look at our first approach. This one is called the sliding window. It's really elegant, it's fast, and it makes a lot of sense. But, and this is a big but, it has one golden rule. It works its magic best when all the numbers we're dealing with are 0 or positive. The easiest way to picture this is to think of a frame or a window that we can slide over our numbers. Now here's the key part. Since all the numbers are positive, the logic is super predictable. When we stretch the window to the right to include a new number, what happens? The sum always goes up. And when we shrink the window from the left, tossing a number out, the sum always goes down. It's this simple, reliable behavior that makes the whole technique work. Let's see this in action. Say our target sum is 5. We start our window on the first number, 1. Our sum is 1. Too small, right? So we expand right to include the 2. Now our sum is 3. Still too small. Let's expand again to include 3. Our sum is now 6. Whoops, we overshot it. So what do? We shrink from the left. We kick out the 1. Our new window is 2, 3. And the sum is 5. Bingo, we found it. And here's what that looks like in code. It's a beautiful translation of the idea. We have two pointers, a left one L and a right one R. The right pointer is always moving forward, expanding our window. But inside, that little for loop is the smart part. It says, hey, as long as our sum is too big, let's keep shrinking the window from the left. It's this little dance between expanding and shrinking that lets us check everything super efficiently in just one pass. So here's the payoff. The sliding window is incredibly efficient. We're talking O of n time complexity, which is just a fancy way of saying it's really, really fast. The time it takes grows in a straight line with the size of our list. And the space complexity? O of 1. That means it uses barely any extra memory, no matter if your list has 10 numbers or 10 million. It's fast and it's lean. Now this all sounds pretty perfect, doesn't it? But what happens when we decide to throw a wrench in the works? What happens when things get a little negative? You see, as soon as we allow negative numbers into our array, that simple, beautiful logic of the sliding window just completely breaks down. That guarantee we had, that expanding the window always increases the sum, is gone.
I love this analogy. With only positive numbers, our sum is like a bucket you're filling with water. You open the tap, the water level goes up. You close it, it stops. Simple. But with negative numbers, it's like your tap is possessed. Sometimes it adds water, but sometimes it reverses and starts sucking water out of the bucket. Now, if your sum is too low, do you expand the window? What if the next number is a huge negative? You're completely lost.
The technical term for this predictable behavior is monotonicity. Our sum was monotonically increasing as we expanded the window. Negative numbers completely shatter that property. Adding a negative 10 to our window obviously makes the sum go down. This means our simple rules of expand if you're low, shrink if you're high are no longer reliable and can lead us to miss the right answer completely. So, we need a different plan. A more robust strategy that doesn't care if the numbers are positive, negative, or 0. Enter our second technique, the prefix sum method, powered up with a HashMap. The big idea here is something called a prefix sum. All it means is that we keep a running total as we go through the array. So if our array is 1, -2, 4, -1, our first prefix sum is just 1. The next one is 1 plus -2, so that's -1. Then we add 4, which gives us 3. And finally, we add -1 to get 2. We're just creating a new list that tracks the total sum at every single point. And here is the aha moment. This is the whole reason we do this. Once you have those prefix sums, you can find the sum of any subarray, no matter where it is, with one simple subtraction. It's just the prefix sum at the end of your subarray minus the prefix sum from right before it started. This little piece of math is the key that unlocks the whole problem.
So think about what this means. We've totally reframed the problem. We're not sliding a window around anymore. Instead, as we're calculating our running total, at every step we just ask a question. To get my target sum, what previous total would I need to subtract from my current total? In other words, we're just looking for a value we've seen before. It becomes a lookup problem.
And how do we make that lookup happen instantly? That's where the HashMap comes in. You can think of it as a superpowered dictionary or a cheat sheet. As we go through our array, every time we calculate a new prefix sum, we store it in our HashMap along with its location. Then, at the next step, we just ask the map, hey, have you ever seen the value current sum minus target? If it says yes, boom, we've found our subarray.
And this code brings that idea to life. We create our map and check out that first line. We preload it with a sum of 0 at index -1. This is a clever little trick to make sure we can find subarrays that start right at the beginning of the array. After that, it's just a simple loop. We update our current sum, check the map for the value we need, and the very first time we find it, we're done. That's our answer.
Okay, so we've seen two really cool techniques. One is a lightweight speedster for a specific race, and the other is an all-terrain vehicle that can handle anything. So how do you decide which one to use? Let's put them side by side. This table lays out the trade-off perfectly. Look at the time complexity. They're both ON, so they're both fast. The real difference is in the use case and the space complexity. The sliding window is your go-to when you have non-negative numbers because it uses almost no extra memory. That's O of 1 space. The prefix sum method is your universal problem solver, but you pay for that flexibility with more memory, since the hash map can grow as large as your array.
And what about finding the first subarray? Well, the sliding window just finds it naturally, because its start pointer only ever scoots forward. With the prefix sum method, we have to be a little more deliberate. We make sure we only store the index for a prefix sum the very first time we encounter it. By doing that, we guarantee that any solution we find has the earliest possible starting point. So at the end of the day, picking the right tool is all about understanding the rules of your specific problem. Sometimes a simple constraint, like non-negative numbers, lets you use a brilliantly simple and efficient solution. But this brings us to the final, bigger idea. These aren't just tricks for one problem. Sliding windows and prefix sums are foundational patterns. They're templates you can adapt to solve a whole universe of other challenges. So the real question is, now that you have them in your toolkit, what are you going to solve next?